right, so last section about polynomials, it deals with complex zeros. And so complex zeros are what we call imaginary zeros. So these are going to be imaginary numbers. So we're going to find all the real zeros, and then now in addition we're going to have some imaginary zeros. So before we get into the polynomials, there's a nice little review about complex numbers. And so everything that we're going to talk about here at the beginning is something that you saw in Algebra 2. You may or may not remember it. If you do, awesome. Feel free to kind of fast forward, skip through the stuff that you remember. If not, and you just want a really good review, we'll just take some time to discuss complex numbers in general. So here's just some simplifying some square roots. So a complex number comes out when you try to take the square root of a negative number. That's just not a possibility in the real number system. And so what's going to happen is we can still perform operations within the imaginary number system. And so instead of just saying, hey, it's complex, we can't do anything, and then we just can't even explore that world of math, there's actually a lot of things that you have to get into the imaginary number system in order to make them work. There's a lot of engineering, electrical type stuff that's true for. And so what you're going to see is just kind of like a basic little intro. So if you are trying to take the square root of a negative number, instead of just saying, oh, hey, we can't do it, we're going to denote that the square root of that negative or -1 is going to be equal to I. And the square root of 36, that's 6. So the square root of -36, instead of just saying, hey, nope, it's out, we're going to call it 6I. Here, the square root of 75, that's not a perfect square, but you can simplify 75. It's 25 times 3. And 25, its perfect square is 5. So a 5 will come out of the square root. The negative can also come out of the square root as an I, saying, hey, this number is now imaginary. It's in a different number system. And left in the square root is still a 3. And you can still perform operations with these numbers. All right, this next one, the square root of -4, that would be 2I, right? The whole thing, 2I. And if you already have a number in the front, you just multiply. So -16I. All right, when you multiply two square roots together like this, you should go ahead and simplify each one kind of independently of each other, and then you can put them together. So the only thing you can do here is bring out the I, so that's I squared is 6. 96 does have a perfect square in it. It has a 4, but I think it has a 16. Yeah, this is 16 times 6. So you can get rid of the 96 and say 16 times 6. The 16 comes out as a 4. The negative comes out of the square root as an I. And left in the square root is still a 6. And then you can keep going here. You would have numbers on the outside, multiply with numbers on the outside, and the inside times the inside. So this would be 4I times I can just be written as I squared. And then the square root of 6 times the square root of 6, that's the square root of 36. And the square root of 36 is just equal to 6. So you can either say square root of 6 times square root of 6 is square root of 36, or you can say because it's the same square root, it's just going to be equal to 6. Multiply, we have 24I squared. And then there's one more thing, and this is the really cool thing about the imaginary number systems, is if you have an imaginary number squared like this, it actually turns it back into a real number. This piece here is equal to -1. And so this would be 24 times -1, which is -24. All right. Next one is a subtraction sign. So we're going to simplify each one separate and then go ahead and subtract. 144, that's 12. And then because it's a negative, it'll have an I. Minus the 100, that's 10. And because of the negative, that will have an I. And 12I minus 10I, it's just combined like terms. That's 2I. All right, and last but not least, this is actually very similar to a quadratic formula type question, but there would have been a plus or minus there, right? Instead, they're just saying, hey, there's just a minus. So we can simplify this square root, and then once we have that, we can try to simplify our numbers in the front. 288, that is 144 times 2. The 144 will come out as a 12, and the negative here will come out as an I. So this will be a negative 20 minus 12I square root of 2 all over a negative 8. And then to keep simplifying, you're looking at the negative 20, negative 12, negative 8, and you're going to simplify those three numbers. This is already simplified, so don't mess with that. But those all have a 4 in them. So I'm going to take out not just a 4, but a negative 4, because that's going to make these signs look a little bit nicer. So that'll be a positive 5, positive 3, still I squared of 2, and then positive 2. So I divided all of those by negative 4. All right, we have some more just operations with these complex numbers. So I have two things being added. The parentheses in this case isn't doing anything because of the addition. So if you just want to rewrite it without any parentheses. And then it really is just combined like terms. So 22 plus 17, that's 39. And then negative 8i and 24i, add those together, we would get 16i. So this is 39 plus 16i. Note that these two are not like terms, right? One has an I, one doesn't. All right, for this next one, it's not a plus sign, it's a minus sign. So that is going to have an impact on both the 17 and the 24. Remember, just like before, if there's a negative in front of the parentheses, you are subtracting both. So we're subtracting 17 and subtracting the 24i. If you mess this up, it's because you have the wrong sign here. So it'll be 22 minus 8i minus 17 minus 24i. And we'll have 5. Put those two together, that's 5. Those two is minus 32i. All right, so that's it for the adding, subtracting. We're going to do some multiplication here. Remember, if you're multiplying with parentheses, you're just going to distribute, right? Some distributing. So negative 3i times 1 is negative 3i. Negative 3i times 7i, that would be negative 21. That's a 1. 21. I, and then it was I times I, so I squared. And then you do need to make the change that I squared is equal to a negative 1. So it changes that negative 21 to a plus 21. And it also gets rid of the I portion there because it turned into that negative 1. All right, continuing on, when you have two sets of parentheses, you do have to distribute like this, right? Multiply it out. It's actually what I like to call it double distribute problem. So 1 times 4 is 4. 1 times negative 2i plus a 4i, and then that would be a minus 2i squared. And if at any point you want to cross off your I squared and change your sign, I'm okay with that. So if right now you know that I squared is negative 1, you can change it and go ahead and make that a plus 2 instead. You could also just write a plus 2 as you're writing that down. And then just combine like terms. So we'll have 6 and plus 2i. All right, and last but not least, we have a triple distribute. So there's a times here, times here, times here. So the key here is to just do like the first two and then put in the second one as you go. So maybe kind of think of these as a separate problem here. Multiply the first two together, get a solution, and then we'll do that multiplication with this one. All right, so we'll have 5 plus 5i plus 20i, and then that would be a plus 20i squared, and because that has an I squared, it's going to change it from a plus 20 to a minus 20. And that's these first two multiplied together. Combining like terms, negative 15 plus 25i. All right, from there, you're going to take that, which is the solution to the first two, and multiply it by the third one. Times 1i, that's just I, right? So we'll have a negative 60, a negative 15i, a 100i, and this last one would be 25i squared, and so instead of positive 25, it'll be a negative 25, and I don't have to write the I squared because that's what changes the sign. So you end up with a negative 85 plus 85i. All right, before we talk about the last operation, which is division, we have to talk about something called a conjugate first. So there is no like actual division operation in the world of complex numbers. Instead, what we do is we multiply by the conjugate. And so the conjugate, literally whatever the sign is on the imaginary portion, you just change it. So for example, this is a plus 12i in the imaginary portion. You're going to change the plus to a minus. You don't change the real part, so 11 is going to stay positive just like it was, but that 12i will change to a minus 12i, and these are considered conjugates of each other. The conjugate of negative 14i, since this is an imaginary piece, you are going to change its sign, so its conjugate would be 14i. The conjugate of negative 5, that's a real piece, and so because it's real, you don't actually change anything. It's still just negative 5. You only change the piece in front of the imaginary, the sign in front of the imaginary part. And so then the last question says, hey, find the product of negative 1 minus 9i and its conjugate. So its conjugate would be negative 1 plus 9i. You only change the number in front of the I. And then the product means you should multiply these two things together. And so go ahead and distribute here. What we're going to get is we'll get a 1 minus 9i plus 9i and a minus 9i squared. And if you're good to go ahead and get rid of the I squared and change that to a plus, and it's not even 9. What am I talking about? 9 times 9 is 81. Don't mind me. So it would have been a minus 81i squared. Because of the I squared, it changes the minus to a plus. All right, and then when you combine like terms, you have 1 and 81, which makes 82. And then this is the whole purpose of the conjugate, is that those two terms in the middle make a 0. They essentially cancel each other out here, right? And so what happens is if you take an imaginary number and you times it by its conjugate, your answer is only a real number. So you can get rid of the imaginary piece there by multiplying by a conjugate. And so what we have here is we have two division problems, and we're going to do this division by getting rid of the i's in the denominator. So the whole point of a complex number division problem is you can't have i's in the denominator. They have to go away. And so in order to get them to go away, we multiply by the conjugate. So on that first problem, the conjugate is 5, but instead of plus 3i, it is minus 3i. And then there is a rule out there that says, hey, what you do at the top, you have to do to the bottom so that you don't actually change the equation here. All right, I'm going to go ahead and multiply the bottom first. 5 times 5 is 25. And then 5 times negative 3i is negative 15i. And then 3i times 5 is a positive 15i. And those two terms, if you set it up correctly, will always cancel each other out and just make a 0. So then the only other piece of this is the 3i times the negative 3i, which would be negative 9i squared. And you can get rid of the I squared and make it a plus 9. So your denominator is just 25 plus 9, which is 34. And so that's the whole point of using the conjugate, is we multiplied the denominator by, it was imaginary, by another imaginary number. But when we did that, it was very specific so that our solution would only be real. All right, in the numerator, you should multiply these by distributing. So you'll have 15 minus 9i. And there's nothing you can do there. It's just 15 minus 9i. So your final solution here, 15 minus 9i, all divided by 34. If those three numbers had something in common, you could simplify them if you wanted. All right, let's go ahead and do this next one as well. If you want to hit pause and try it on your own, go for it. The goal here is to go ahead and get rid of any i's in the denominator. So you're going to multiply by the conjugate. which means instead of a plus 4i, it'll be minus 4i. And you have to multiply by the same thing in the numerator. I like to take care of the denominator first because that was the one that we set up, right? So 6 times 6, that's 36. And then 6 times negative 24i, or negative 4 is negative 24i. And then you have the positive 24i here. So those two terms will cancel each other out. And then at the end, you have 4i times negative 4i, which is negative 16i squared. And the I squared changes the negative 16 to a positive 16. So that denominator is 52. All right, multiplying in the numerator, we would have 24 minus 16i plus 12i minus 8i squared, and you can get rid of your I squared and change the minus 8 to a plus 8. So combining like terms, there would be 32 minus 4i. All right, and if these three numbers simplify, you can simplify them. 52, does it have a 4 in it or no? All right, it does have a 4. So what we can do is we can divide all these numbers by 4. So 32 divided by 4 is 8. 4i divided by 4 is just an I, or 1i. You can put the 1 in there. And then 52 divided by 4 was 13. So here is the simplified version. All right, so what we're going to do now is we're going to go ahead and start working with these complex numbers in terms of polynomials. So talking about polynomial solutions. All right, so let me get this set up better. So this first one says, find a degree 3 polynomial with real coefficients having zeros at 5 and 3i and a leading coefficient of -1. So let's talk about the zeros. If there's a 0 at 5, that means there's a factor that says x minus 5. If there's a 0 at 3i, then there is some factors that we can make from that would give us that 0. And so there's kind of a couple ways to think about this. So one thing you could do is you could set up a factor here. If it's 3i, it would be x minus 3i. You would change your sign. And then there is a rule out there that says, hey, if you have an imaginary number, its conjugate is also a solution. And so that would mean if 3i is a 0, then -3i would also be a 0. So you could set up another factor as x plus 3i. And then what you would have to do is you would have to multiply this all out. And because these are conjugates of each other, you're going to get the i's to go away, which will leave everything with real numbers. So that's kind of option number 1. This isn't a bad option for this problem in terms of the multiplication. But when we get into maybe this next question, where if you see this 0 is 4 minus 2i, that's going to make this multiplication a lot more difficult. So I'm going to kind of show you another way to go about this 3i piece here, as opposed to just multiplying it out and going from there. So kind of off to the side, if x has to be equal to 3i, what you can do is essentially work this backwards. Another way to get rid of an I is to raise everything to the power of 2, because I squared changes back into a -1. So if you square this side, you can do that as long as you square the other side as well. So this would be x squared equals 3 squared, which is 9, and I squared, which is I squared, but we know I squared is a -1. So it would change your 9 from a +9 to a -9. And then moving this back over, I squared plus 9 equal to 0. That means that this would be the factor. So if you were to actually multiply these out, combine like terms, you would get x squared plus 9. And so 2 ways. You can either write it as your factors, multiply it out to get your x squared plus 9, or you can set it equal here and try to work it backwards, get it equal to 0, and that would also give you a factor. The other factor is still the x minus 5. So to find the actual polynomial, you do have to multiply these ones out here. So x times x would be x cubed plus 9x minus 5x squared minus 45. And if it bothers you if they're not in the right order, you can set them up by just flip-flopping, right? So here is your third degree polynomial, real coefficients, all the numbers are real. It has these zeros because we set it up that way, and a leading coefficient of positive 1, and leading coefficient's positive 1. All right, so here's the next one, a little bit harder based off of the zeros. So it says, once again, find a degree 3 polynomial with real coefficients having zeros at x equals 3 and x equals 4 minus 2i, which also means that 4 plus 2i is an option as well, right? The conjugates. So if this one's a 0, this one has to be a 0 as well. And leading coefficient. And then it says write it in expanded form, not factored form. So for starters, the x equals 3 would come from x minus 3, right? And whenever you go to write an equation, it's easiest to write it in factored form, and then we'll just distribute for that piece. For this other 0 over here, your option would be x minus the 0. So like that. And then you could set up the next one, x minus your other one, which is your conjugate, like that. And then you could distribute here and multiply this out. And this is where this gets a lot more complicated. You don't really want to try to mess with that. So the easier way, once you get into this type of zeros that have multiple pieces there, is to just work it backwards. All right, so I picked one of them. I picked 4 minus 2i, and I'm going to work this backwards. So I'm going to square this, but before I square it, I want to move the 4 over because that's actually going to be easier on the squaring piece here. So I subtracted 4, and then now I'm going to square both sides, and the reason I square both sides is to get rid of the I. So over here on this side, you'll have negative 2 squared, which is positive 4, and then it will have an I squared with it, and we know I squared is equal to negative 1, so it changes that positive 4 to a negative 4 over here. On this side, you do have to multiply out x minus 4 times x minus 4, which is not bad. You've been doing that for years now. So x squared minus 4x, so minus 8x plus 16. And then last but not least, get that 4 over, so it is equal to 0. So we'll add 4, so that'll be plus 20 equal to 0, which means that this is what you would get if you multiplied this out. You would get x squared minus 8x plus 20. And this process here on this side is a lot easier than actually multiplying what's going on here, because this would end up, you'd have to multiply the negative first and here and the negative in here, and then you'd have to multiply each term in this factor by each term in this factor, and you'd end up with 9 factors, and then you have to combine like terms, and it would get kind of messy. And so you're more than welcome to do it that way if you want, but I would highly suggest working it backwards this way. It's going to make it easier. All right, the other factor here is still the x minus 3. And so we're going to get our polynomial in expanded form by distributing here. So we'll have x cubed minus 8x squared minus 60. And then distributing in the negative 3, negative 3x squared plus 24x. And I messed this up. Don't mind me. Let me fix this. I'm just going to start over because I just know I messed it up somewhere. So x cubed minus 8x squared plus 20x, there we go, minus 3x squared plus 24x minus 60. Okay. And combine like terms. So we'll have x cubed. We'll have a minus 11x squared, a plus 44x, and a minus 60. All right, so there is, sorry you couldn't see that. So there is the third degree polynomial, all the real coefficients. It has the appropriate zeros because that's how we set it up. Leading coefficient of 1, and it is written in expanded form instead of factored form. Note that you have to go from factored form to expanded. You can't just take these zeros and just write it like this. That's next to impossible. You have to go through factored form. All right. Few more problems from this section. We are going to find all the zeros of this polynomial. And by all, it means all the real and all the imaginary, so finding them all. And so what we're going to do is we're going to use our possible rational zeros. We're going to, possible rational zeros, use synthetic division, and go ahead and use the quadratic formula or another rule that we might know, another factoring, something like that, to solve the quadratic at the end. All right, so this one's really nice because we have a 1 at the end and we have a 1 here. So our possible zeros, the real ones, are at the factors of 1, which is plus or minus 1 from the constant term, over the factors of the leading coefficient, so plus or minus 1 from here. And if you do the division, you only have two options. It's either 1 or negative 1. And so if you grab your calculator, or you could do this in your head, right? One of the two would work. I'm going to try 1, and I'm going to see what happens. 1 cubed is 1. 1 squared is 1. That's also 1. So it's 1 minus 1 plus 1 minus 1. So it's 0 and 0. So that is 0. So we know that there is a 0 at 1. And then putting your coefficients here to set up for your synthetic division, just make sure you have the positive negatives, right? So it's 1, negative 1, 1, and negative 1. First number comes straight down, multiply, add, multiply, add, multiply, add. And that 0 at the end is your remainder. So because there was a 0 at the end, that is good news. All right, and then the polynomial at the end, if we started with a cubic, this would be a quadratic, and then plus that. So I would have 1x squared, so I'd have an x squared plus 0x and plus 1. So I know one of the zeros is at 0, I know one of the zeros is at 1. The other ones come from here, so we're figuring out where is this equal to 0 at. And your options, you can try to factor, you could quadratic formula, you could complete the square, or in this case, because it's missing that middle term, you can just use the square root property where you subtract 1, take the square root. Whenever you take a square root to solve, you should include plus or minus. So this would be plus or minus the square root of negative 1. And the square root of negative 1 we have talked about in this section is I. So the other zeros are plus or minus I. So there's 3 zeros. One's real at 1, and there's 2 imaginary, I and negative I. By the way, I and negative I are conjugates of each other, right? All right. Given P of x equals x cubed minus 64, write P in factored form as a product of linear factors. So I don't know if you recognize this, but this is actually factorable. But if you don't know how it factors, if you don't remember the rule from Algebra 2, then that's not really going to help you. So if you know what I'm talking about and you know how it factors already, then you take that shortcut and you go ahead and factor. And you're going to end up in the same place we end up after we do a little bit of work. But if you don't remember how it factors, that's okay. You can still use this process of finding a possible 0, set it equal, or find the synthetic division, right? And then quadratic formula, all that fun stuff. So here's the possible zeros. It's factors of 64. So 1 and 64, 2 and 32, say, is 4 a factor? 4 and 16. And then 8 times 8, right? 8 times 8. And then this would be over the factors of 1, which is just 1. And so it's plus or minus of all of these. So here's your options. You could have plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8, plus or minus 16, plus or minus 32, and plus or minus 64. So is each of these divided by 1, and then it's the plus or minus version of them all. And so one of those numbers is going to give us a 0 in here when we plug it in. If you're not sure, just go ahead and start plugging them in. Because this is a cube and it's subtract just one number, there's actually, you can kind of think about this maybe before you just blindly plug in numbers. 1 cubed is 1, so that's not going to work. 2 cubed is 8, so that won't work. 4 cubed is 64. So I'm going to just start here with, it's either a 4 or a 6 or a negative 4 to make this happen. So 4 cubed minus 64 is equal to 0. So the 0 we can use is the 4. So we're going to synthetic divide out the 4. So in terms of coefficients, starting with a cube, we have 1. There's no x squared, so that's 0. There's no x, so that's also 0. And then that last number would be 64. First number comes straight down. Multiply, we get 4. Add, we get 4. Multiply, we get 16. Add, we get 16. Multiply, we get 64, which add is a 0. So that is good news because it is an actual 0. All right, and because we had an x squared or x cubed, now we're going to go with x squared plus x and then constant term. All right, so x squared plus 4x plus 16 is what we currently have. So because it says write it in factored form, that's currently a factor. The other factor is from the 0 at 4, so it would have been x minus 4. If you knew how this factored at the beginning, remember I said if you know how it factors, factor it, you end up right here. So you should have this. If you know how that factors, you just jump straight to this. So you get to skip all of this. If you want to know how it was supposed to factor, that is what we call a difference of cubes. So you could factor that with a difference of cubes. By the way, the last problem you could actually have factored by grouping as well. But if you don't remember those techniques, that's okay. All right, it does say factored form. It is currently in factored form, but then it says as a product of linear factors. And technically, this second one here is not a linear, it's a quadratic. So we have to keep going. We either have to factor this or we have to quadratic formula it. Somehow we have to break this down into the solutions or the further factors. All right, thinking about it in terms of factoring two numbers that multiply to be 16 and add up to be 4. Your options are what? 1 and 16, 2 and 8, 4 and 4. So that's not going to work. So you're going to have to use the quadratic formula. So for quadratic formula, it would be x equals negative b plus or minus square root b squared, so that's 16, minus 4 times 1 times 16. So if it's ever times 1, you don't have to put the times 1 on there. All over 2a, so all over 2. All right, so 16 minus 4 times 16 is negative 48. So we have negative 4 plus or minus the square root, negative 48, all over 2. Continuing to simplify this, the 48 has a perfect square in it. That's 16 times 3. So this would become negative 4 plus or minus. The 16 comes out as a 4. The negative comes out as an I. Square root of 3, all over 2. And then the numbers on the outside, not the one in the square root, but 4, 4, and 2 all have something in common. They all have a 2 in common. So we can say negative 2 plus or minus 2i square root of 3 all over 1. And that's not necessary to say all over 1. So the solutions to this is this one. And so this is where some crazy factoring writing is going to come back into play. So we're going to start, we have the x minus 4. That's the first factor. And then these other factors will be x minus your solution here. And it's easiest if you just put those in parentheses. Your solution is negative 2 plus 2i square root of 3. And then x minus negative 2 minus 2i square root of 3. And then these are considered linear. So when you find your solutions from the quadratic formula, it's x minus the plus version and x minus the minus version. And if you just put those in parentheses like that, then you won't have to worry about getting your signs all correct. All right. That one's definitely a hassle for sure. A lot going on there. Last question in this section says find all of the zeros of the function, and then it gives us a fourth power function, and so we're going to be looking for all the zeros here. The first thing that I notice as I look at these is all of these numbers are even, aren't they? 4, 16, 2, negative 2, 24. So I can actually make life a little bit easier by dividing them all by 2, by taking out a GCF of 2. It doesn't change the x's, but it changes the coefficients. And what's going to happen as I make my list of possible zeros is it's going to make a smaller list because I'm working with smaller numbers. All right, so here's the list. Factors of 12, which would be plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, and plus or minus 12. So 1 times 12, 2 times 6, 3 times 4. In the denominator, we have a 2, so that's just plus or minus 1, plus or minus 2. And so if you were going to make the full list, you would have plus or minus 1, plus or minus 2. I'm dividing them all by 1 right now, so that's not going to change anything. 6 plus or minus 12. And then you can divide them all by 2, so you'll have a 1/2. 2 divided by 2 is 1. You'll have a 3/2. 2, 3, and 6, and those are all on the list. So here's our total list of possible rational zeros. And now what we have to do is we have to check. We are looking until we find one. So grab your handy dandy calculators. I'm going to start by doing a bunch of positives, and we'll go from there. Once again, if we were in class, we would tag team this, and it wouldn't take us nearly as long. Minus 16, 1 to the power of 3. I'm putting in 1 right now. And minus 24. I do not get 0. So I'm just going to hit up, go back and change all the 1s to 2s, and try again. I also do not get 0. So hit up, change the 2 to 3. Once again, do not get 0. Changing to a 4 now. I do not get 0. Changing to a 6. So I realized I missed a term. So all of those checks weren't very good because I forgot my linear term in there. So I'm going to have to start this over. Sorry, y'all. So 4, and then to the power of 4. Got to make sure we plug it in right. Power of 3. And then plus 2, 1 squared. And then this is the one I missed. Minus 2 times 1. And then minus 24. There we go. So now I should be good. So I'm testing 1. I hate that light is literally right there. So testing 1, It didn't work. I got a 36. So now I'm going to retest 2. All right, 2 doesn't work. So I'm going to test 3 again. Sorry, I had it typed in there wrong. 3 doesn't work. Testing 4. And 4 does work. So I knew I had it typed in there wrong because I knew 4 worked. And so when I did it the last time, I was like, wait, 4 doesn't work? 4 does work. So we have ourselves a 0. So we're going to synthetic divide out 4. When you do this, I know I use this in my calculator to test. You could also go based off of this one if you wanted. I'm just going to go straight back to the original function when I go to do the synthetic division. You don't have to. You could use this one as well. So completely up to you. -2, -24. So bring the 4 down, multiply, add, multiply, add, multiply, add, and multiply, add. And I get a 0 at the end. And so because I started with an x to the 4th, I'm going to have an x cubed now, an x squared term, an x, and the constant term at the end. So here's my new polynomial, 4x cubed plus 0x squared, so plus 2x plus 6. And so I have to keep working with this guy. In terms of finding another 0, right, because we're still at a cubic, so we still have to find one more to get it to a square. And then once I have the square, we can quadratic formula. You can either go based off your list again and keep testing values, or you could take a look at this and make a new list. One thing I noticed is that they do all have a 2 in it as well, right? So if you divide them all by 2, you'd end up with 2x cubed plus x plus 3. And it might be easier to start over with a new list here. Or you could go ahead and just continue on your list that you have here. So if it has another rational 0 here, it's already in this list up here. Let's go ahead. I'm just going to continue because I already have it in my calculator. So I had 4. So now I'm going to try 6. And see if 6 is another one, because we got to get it down to a quadratic. 6 is not. So now I'm on 12. And when I go to put this in, I'm going to have to, because it was only 1 digit before, I'm going to have to hit the insert key to get to 12 so that it doesn't erase it. So I'm going to be a little bit more careful here. So instead of 6, hit 1 and then insert a 2. And then 1, insert a 2, and then 1, insert a 2. And then if you want to scroll back through to make sure you have it all, that you didn't delete it or anything. If you don't like to do that, you can always just retype it in with the 12. Definitely not 12. Before I get into the fractions, I'm going to go test the negative versions of these. So the next one's -1. So I'm going back to the beginning and trying -1 now. The nice thing is, because I have 2 digits in there already, I can just hit -1 over top. -1. Hey, and look at there, I found another 0. So it also crosses at -1. So, running out of space. Let me grab another sheet of paper. Hold on a second. All right, so we're going to continue on here. So I have -1 as well. And I'm going to keep dividing. You can use these coefficients here, or you can use either of these, anything here. Do not go back to the original because you're not going to make any progress. I'm just going to go based off of these coefficients here. So 4, 0, 2, and 6. So whatever the coefficients were at the end of my last synthetic division, I'm just going to use those to continue on. So the 4 comes straight down. Multiply, add, multiply, add, multiply, and add. And we do get a 0 at the end, which is good news. So because these came from the cubic here, that means that this is now an x squared, an x, and just a constant term there. So my new polynomial is 4x squared minus 4x plus 6. All right, one thing I notice again is they all have a 2 in it. So I could simplify this to 2x squared minus 2x plus 3. And I want to figure out where does this equal to 0 at. That's going to give me the rest of my zeros. And your options are you could factor, you could complete the square, you could quadratic formula this. Thinking about the factoring real fast, times, they would be 6, add up to be -2. There's not two numbers that multiply to be 6 and add to be -2. So that kind of implies quadratic formula. So x equals 2 plus or minus square root of 4 minus 4 times 2 times 3 all over 2a, so all over 4. So we have, for the discriminant, 4 minus 4 times 2 times 3, that's -20. So I have 2 plus or minus the square root of -20 all over 4. Working from there, 20 is 4 times 5. So 2 plus or minus, the 4 comes out as a 2. The negative comes out as an I. Square root of 5 all over 4. And then these simplify. These 3 terms in the front, they all have a 2. So it'll be a 1 plus or minus 1I square root of 5. You don't have to put that one there because you have extra terms. All over 4. And then it doesn't simplify anymore. So we have made it to the end. So find all the zeros. This is a 0 here. There's 2 technically. They're imaginary. And then go back. You had one at -1, and you had one at +4. So -1, +4. Those are all your zeros. All right, I know these problems are a little lengthy. They take a lot of work. As you're working in My Open Math, if you get stuck on something, please message me so I can help you. It's actually best if when you message me, you take a picture of where you're at so I can direct you further. Just saying, hey, I got this wrong is not very helpful because look at all the places you could have made a mistake at. And I'm not that good where I can be like, oh yeah, you got -3, but the answer was -4. This is exactly where you messed up at. And so if you've done a ton of work, if you would send me your work, or if you just wanted to wait till you're back in class, you could ask that as well. That's fine. But definitely stay organized and have your work in spots, because if you say I'm stuck on this one or I can't get the right answer, I'm gonna be like, where is your work at? So just kind of know that these aren't going to be ones where I'm going to want to start from the beginning every single time. I'm going to want to start from wherever you're at and see if we can figure out where the mistake happened. All right, that's all I have, and that's the end of our polynomial discussion. So good luck on the homework.